You want me to start? Oh, here we go.
Okay. Good morning, everyone, and good morning, Charlie. We are happy to have you for the session 2 of your presentation. Welcome.
Thank you. Shall I start rolling?
Yes, please.
Okay, so previously on the Exponential, the rabbit hole and the engineer, I told everybody I was going to talk about 3 lessons that we learned about sustaining complex systems, or maybe lessons that we consistently relearned about useful things to do. And I limited it to 3 lessons because we don't have time to talk about everything. And then I introduced this idea of systems can be anything from purposeful man-made systems to non-man-made systems, or even systems that we didn't intend to have a purpose, like the Spanish flu. And then this is the overview charts where it says I'm going to talk about my career, what I learned about systems and complex systems, and what is sustaining complex systems, and then the lessons. And so we got about halfway through this last time. And this is the charts I included for any of the young folks who might be interested in getting advice from an older guy. This chart introduced my family and the fact that they supported World War II. It also shows, my credentials and background and the things we're going to talk about today, some of my experiences in aerospace that led me to sustaining complex systems and understanding what it was all about. And let's see, and introducing my family, my dad and my uncle, who fought in World War II, and surprisingly, because of their participation in proving the concept of strategic bombardment, left us all with a completely different world where we needed to have deterrence. So I talked about the system of a combat box and a flying fortress, talked about the logistics system, and then I talked about post-World War II, leaving us with an entirely different world where we were no longer protected by our oceans and had to come up with the concept of deterrence. And then talked a little bit more about how systems were starting from, I would say, this curve here is meant to say that back here about 1790, we started to develop a lot of complex systems with the Industrial Revolution, and they have just grown exponentially in numbers and in how long they live. And so if you were never a sustainment engineer before, you probably will be soon, because there are so many complex systems out there nowadays that need to be sustained. And this chart talked about how when I got into the job of being a systems engineer on ICBMs in the mid-80s, they were just at that point transitioning from, as you see on the bottom, rapid prototyping all sorts of different ICBMs to really settling in on Minuteman III. And we focused here in Utah on sustaining that to the best of our ability until the latest missile can be deployed, the GBSD, which I'm sure you've all heard about. And so I think I got about here where I was explaining that this is the model that we followed, that we developed and followed in the mid-80s and forward. And what we found was that when we stayed focused on this model and we kept this culture going within our sustainment team, which included TRW, the associated contractors, the government, if we focused and stayed on this model, we probably only have one major crisis a year. But if we strayed from this model, we kept getting surprised too much. And so we worked hard over in TRW to try to make sure that we were inculcating this into our culture. And what is this? Well, obviously you have to identify risks if you're going to keep going, identify risks to your ability to sustain, not just focused on sustaining your complex weapons system, but if you look to the left there, I could use this cursor. if you look over here, this is a purposeful system, one with a mission, that of deterrence. And we have operators who are in the loop on this system to make sure that deterrence happens. And for ICBMs, we knew that if we could stay reliable, available, accurate, and hard against nuclear attack, and safe and sure, these were our readiness factors that we needed to stay focused on. So for instance, if you're sitting in your monthly risk management meeting and somebody says, we have this problem, we have this emerging failure mode in this area, probably the next thing somebody's going to ask from the front table is, well, which of our readiness factors is this going to affect? Does this mean we're not going to be reliable in flight? Does this affect our accuracy? What sustainment readiness factor are we dealing with here? And I also mentioned last week that in order to be able to identify risks, you have to be able to observe your system. Just classic control theory. If you can observe your system, then you've got, that's sort of the yes, no on whether you can control it. So for instance, I'll just throw in an example today. We hear from the folks who are trying to make fusion happen, limitless free energy, that they're finding that by using a neural net AI type of control system, they're able to control the fusion and make it happen longer and longer periods of time. And so just like in classic control theory, if you're going to identify your risks, your system, you have to be able to observe your system. And so we had a huge assessment program where we looked at not only, of course, we couldn't wait until the missiles launched 3 or 4 times a year, but we went down that rabbit hole of indenture, and we would look at what's going on in our repair depot. What are we seeing in our little resistors that we pull off of the boards? Are they degrading in a certain way that might tell us something about an emerging failure mode? For those things that are difficult to get to out in the silos, where we've got liquid 4th stage in a warehouse, or we have some solid stages we pull from their remote sites and bring into Hill Air Force Base. We do regular periodic inspection of all these things to see if we can see either emerging failure modes we didn't expect, or we can see that those things we do expect are actually degrading along the timeline that we expect them to, or they're faster or slower. So that's the observe readiness piece. And then of course you need to come up with a plan to fix your system. And when you're doing that, you're taking all of your identified risks and you're coming up with a fairly long list of emerging failure modes and risks that you need to deal with before they affect your readiness factors and your mission. And so in order to do something about that, you have to come up with mitigations. And of course, we all know that whatever risk mitigation you come up with introduces, perhaps little additional risk. When I was a software manager, we sort of quantified that as it seemed like about 5% of the fixes to our software created another problem. And so you've got that to deal with. But more importantly, when comparing what we did with ICBMs to what we're going to be doing in commercial space, is this idea that we're so remote, buried out in the northern tier, that we better collect a bunch of our fixes together, come up with an integrated systematic plan, so that when we go out there to those silos to make our changes, that we're not having to visit and revisit and go back more often and waste a lot of money and make our system unaffordable because we didn't put a little thought into going out there all at once to do the work. And so that should apply directly to the sorts of things you need to think about, whether your ground systems are remote or you've got to get up into to space. Of course, we've proved in the last few years that we do have the capability to tug around orbit and deliver fuel to satellites and things like that. So So that age isn't just coming, it's upon us now. And then I mentioned last time I showed that it's important, willing to speak up and tell you here an emerging about the battery. You need to be able to handle. And we were doing this back in the mid 80s, and then going forward, we even instituted some. Are you able to hear me okay? Everything's fine. I just got a warning notice that my internet's possibly giving me trouble.
Yeah, there were some breaks. Mhm.
Okay. Well, if that continues, I could try switching to cell, but probably if we have a dropout here from our Xfinity network, we're just out of luck.
It got restored, I think. It's back
Yeah.
to normal.
Okay, and I was on a roll too, talking about big data. We handled a lot of big data, but we also came up with new ideas of how to survey the ICBM. So for instance, every month we test every ICBM to make sure that the stage one nozzles move correctly. And part of the reason, there's lots of reasons to check that, but one of the reasons is that's one of those systems where we know after a certain period of time, the hydraulic oil in those nozzles, in that control system in those nozzles, gets depleted. And we sort of know, generally speaking, how long that takes before we have to get out there, pull that stage one, which is a big operation, and recharge those hydraulics. But what we came up with was a new way of looking at that by taking the data we already had coming from those missile tests, analyzing, collecting huge amounts of it, analyzing it using our newer data systems tools to sort of predict that curve of when we're about to run out of oil, so we could actually better schedule the pull of that stage one and the replenishment of that hydraulic oil and refurbishment of those flight controls. And then I mentioned also that we had to make sure that we had very good disciplined approaches throughout all of the decades that we were sustaining, so that when we're comparing, so you can imagine every once in a while, actually all the time, we're drawing these charts that show the physical changes in the system. And that chart only means something if you're looking at it and testing it the same way, exact same way every time, or you understand the differences. And so that's the importance of making sure you've got very disciplined processes where you do it the same way every time. I was going to say something more about that, and if I think of it later, I'll backtrack. But let's move forward now to some of these other things I wanted to mention. A lot of times when I say the word sustainment, people think of the word sustainability because that's, of course, a gigantic buzzword right now. You certainly want to eat your sustainable tilapia. You want to make sure that your farming is sustainable. Everything that we do nowadays, we're thinking through a filter of sustainability to make sure that now that we're not only now that we're out there, well, let me put it this way: sustainability is kind of like reliability and maintainability and survivability, and that your best shot at sustainability is to think about it as you're designing whatever system. If you're deciding to be a farmer in Utah right now, you might want to think about those indoor farming buildings where you conserve huge amounts of water by doing your farming inside. It's more sustainable because we're going into an era now of massive drought in the West. And so people are applying this concept of sustainability everywhere because we just have to. But that's not what I'm talking about when I talk about sustainment. I'm talking about the old days in 1985 when Air Force Systems Command had a very complex weapon system that they had completely finished developing and had fielded, and the operators, the weapon weapon system operators and the warfighters are out using it. And now it's outside of the purview of systems command, who develops systems. And it's now in the purview of logistics command, who sustains that system. And one of the really interesting things that occurred back then, now I guess I have to sort of take a side note here and say that was then, and that way of doing things definitely had flaws. It very much felt like you were throwing a very complex system up over a wall, where us guys, for instance, like at Hill Air Force Base, would catch it and suddenly find this mess in our hands that we had to deal with. And, but that was our job. Since then, we've become more enlightened, and we have a systems command that includes the entire life cycle. And you've got a special, Air Force level group of people that think about sustainment all the time. But back in those days, it very much felt like you were catching a pile of crap that you had to deal with. And one of the things that we learned over time as we sustained more and more of these complex systems was there's this new sort of thing that happens when you've deployed your system and the warfighter is using it, and emerging failure modes are showing up and you're having to go make fixes, is that you're no longer working as much to your design baseline as you are working to this thing that we started calling the capabilities baseline. And the capabilities baseline for a deployed system is what the operator is expecting. If you fix something and you do it in such a way that you surprise the operator that he's now lost a capability that he was expecting to have, a capability that never appeared in any of the design documents, that person is not going to, oh, well, it's not in the design documents. Well, that's okay. They're not going to say that. They're going to be all over you about ruining their mission. So you had to have a very close connection between yourself as the sustainment engineer and the people that are using the system and what they're expecting out of it, so that as you're maintaining it, sustaining it, making modifications for whatever reasons, you're not impacting their mission. The other thing, of course, that happens with every decision maker, and we saw this very much during the recent pandemic, is that you're always trying to make very critical decisions with not enough information. And what you're hoping for by keeping a close eye on your system, trying to understand the physics and the science behind the degradations that you're uncovering, is that you're hoping to be able to draw a physical model that you can extend a little bit in the future and therefore predict the future, which is of course impossible. But so you usually don't have enough information. You're trying to predict the future, but if you do it in the right way, you can at least, you may not be precise, like might not be able to say how many people are going to die from the pandemic in the next 6 months, but you might be able to say it's going to get worse over the next 6 months, and here's some things we ought to be doing. So, and that's exactly what we did with ICBMs, is we took our best shot at it, trying to give us enough time. There, the third bullet, risk and time factor. I'm right here in case you didn't know. The time factor that says, okay, we need to detect this early enough to come up with a fix and deploy that fix. And oh, by the way, there's always a chance that whatever we did might create another problem. So how much time should we be allowing for this? And you factor that time in when you're doing your list of risks and what you're going to tackle first, second, third, fourth, fifth. One of the things we did back in the day of systems command and logistics command and strategic air command was we would hold high-level conferences with those three major entities, because sometimes the fix that you came up with was so big that we would send it to systems command to go implement. But you would take those three entities with their 3 4-star generals, and you'd get them all to agree on the top 10 list of things that you had to go do next on ICBMs, so that all three of them were coming to the Pentagon bucket of money with the same story. And so, of course, one of the things that we had to focus in on as good managers was making sure that the people telling our story at the Pentagon understood the story and could relate it. So anytime we did that better, we were better off. Now, it's interesting that we see things like pandemics and the, say, climate change, things like that. You don't have a board of generals that sit there and make a decision. Closest thing you get to that is sort of like, maybe the dictator of China, who can convince his backers that we need to go build a lot of nuclear power plants and we need to start right now. But you don't see that worldwide. And especially in America, we could think about the fact that the people holding the purse strings are the general public. And so you need to not only be able to explain, like in ICBMs, you had to take a very complex situation and explain it to a guy who was, his whole career was a fighter pilot. And now he's in charge of this very complex system. But we had a saying back at TRW was that if you can't explain it simply to your customer, then you don't understand it. So you need to go back and study it some more. So if in the same thing will apply in the case where the voters get to decide, you need to be able to explain it to her. It's kind of go back to that old Winston Churchill quote, where he said during World War II, he said, the Americans can be counted upon to do the right thing after they've tried everything else, right? So you have to kind of eliminate them trying everything else, or at least make sure that you've got the solution there ready when they're ready to hear it. Some really great solutions out there right now, by the way, for climate change that you're not hearing about from congressional leaders or the public at large, because they haven't heard about them yet. So there's that whole factor of sustaining complex systems that we didn't have to deal with, but it sort of shadows this idea of, making sure the decision makers get the simple understanding of what the risk is and what we need to do about it, and where it stacks up with all the other risks. So I'm going to talk a little bit about my career in order to sort of reinforce this idea of systems. And coming right out of the Air Force Academy, my first assignment was in-flight refueling SR-71s worldwide in support of deterrence, which I had mentioned earlier. So right away, right out of the chute, I get to have a very responsible job, first being a crew member and then being the aircraft commander in that tanker. I'm talking about the guy flying this thing here. I'm the guy flying that tanker. And bottom line is, if you don't deliver the gas, then the Joint Chiefs of Staff don't get their intel on the missiles and bombers that our adversaries have and what they're doing with them and where they're putting them. Cuba is a major example of this. So that sort of opened my eyes when I first started doing this job. I started to realize, well, we've got these KC-135Q model tankers, which are specially modified with super secret stuff and special fuel systems and special training for the crews to be able to support this SR-71. And in order for that KC-135Q to exist, somebody had to design it, sustain it, maintain it. There's all sorts of people in all of those roles, along with all the logistics of supporting that aircraft before you even get to the receiver, the SR-71, who everybody notices because it's the fastest air-breathing manned aircraft that ever existed, perhaps ever will exist, because after the SR-71, the things that go faster started, going up into space. But so that sort of started forming in my mind this idea that in order for my mission to be accomplished, to get that reconnaissance to the top leaders in the nation, then we needed to have a very complex system. And that complex system, if you're going to try to sustain it and support that mission, you need to, as a sustainer, understand where do you draw that circle around your system so that you capture everything. I think I mentioned last time that one of our issues with ICBMs was there's real property associated with the launch sites up at the bases on the northern tier that can affect the mission if you don't keep an eye on it. So our risk management meetings would include people from the base, despite the fact that they weren't really part of the official organization of sustaining ICBMs. But that was, one of my first lessons about systems, and so let's move forward to my next assignment, where I worked in the Air Force Space Program. And this is a fascinating. Now, each of these individual charts I mentioned last time really have a whole nother presentation behind it that you can find on my website, which is listed on the first chart. So when I went to my next assignment, because of my degree in astronautical engineering, I was assigned to the Air Force Space Program as a software manager. So this would have been 1982. So if any of you can remember what software management was like in 1982, it was an emerging understanding of what does it take to sustain software. And so, all of us were sort of finding our way through that. But one of the things that I learned, and one of the great things about being in the software area, is that, of course, software touches everything in your complex system. So you learn the whole system as you learn the software. In this case, I was the software manager for the inertial upper stage, which is this piece right here. Some of you might remember the history about we were thinking that we would be putting liquid fueled Centaurs in the back of the space shuttle, because that was the sort of fuel that it would take to lift these heavyweight geostationary spy satellites and interplanetary missions. It would require that much energy to push up into that realm. And it also had to not only fly on top of a Titan 3-4D or a Titan 4, but it had to be able to fly inside of a shuttle. And of course, after the first shuttle disaster, we pretty much decided in the industry that we weren't going to be putting a liquid fueled bomb in the back of a space shuttle. And so what started as the interim upper stage, sort of a two-stage solid rocket, very much like a shortened Minuteman ICBM, Boeing made them both, that would have to suffice. And this is no longer going to be the interim upper stage, it's now going to be the inertial upper stage. And so people started thinking, well, this is going to be around for a while. We need to have a plan for sort of sustaining this capability. And one of the plans that people were trying to make happen was this idea that if only the payload and the launch vehicles would realize that the inertial upper stage is a standard, and they would build their systems to that standard, then we could use that IUS in a lot of missions for a lot less money, and it would be a kind of sustainment cycle at that point. Now, that never reached full fruition, and I think probably those of you who thought about it a couple of seconds realize why. The superstars in the space, in NASA, in the Air Force especially, the superstars are those highly classified satellites. And if they've got a special requirement for a mission, they're not going to say, well, we can't do that because the IUS won't do it. They'll go back to the IUS and they'll say, you need to modify your software so that we can control this stack in such a way that we can get this thing up into geostationary orbit, or we're going to have this planetary mission. We think it's coming on the horizon. Can you add a third stage and fly that thing off the top of a Titan 4? So you had to be able to be flexible and make a lot more changes in the IUS than we kind of thought would be appropriate for trying to have a cheap upper stage. But in retrospect, looking at it now, I think we did a darn good job, because over 20 years, we flew about 24 missions. And so that's been a standard high energy upper stage for quite a long time. Well, like I said, I've got another presentation on that you can go look at on my website if you're interested in some of that background. So that's my first two assignments. And then I left active duty, I got a job with TRW working on ICBMs. And I put a picture up here of my friend David Stump's book, which came out a couple of years ago, I think, which is the definitive technical history of the Minuteman missile. That if you're interested in learning more about this particular complex system, I suggest you buy that book. It's a great book. But I'm going to talk a little bit about when I went from working in Space Division to working at TRW. You get sort of indoctrinated into this concept of systems engineering. And I mentioned the history last week about how TRW basically took Bell Labs systems engineering from its infancy and brought it through adolescence, because we needed to be able to do things like track requirements down to the lowest part and then validate those requirements as we design the system. And then, of course, if you're sustaining the system, you need to remember about those watershed requirements. My first assignment in ICBMs was with training devices. We have so many Air Force, 19-year-old Air Force enlisted folks sustaining this nuclear weapon, that somebody early on thought it would be a good idea that their first hands-on experience with it would be a training device and not the actual thing. And so we had we talk about a complex system, we've got a whole branch of things for Minuteman ICBMs, which are training devices that have their own set of systems engineering requirements to make sure that they faithfully train these young kids. Now, my assignment in training devices, my first assignment, I always like to say this because I think it's kind of a hoot. Down at the bottom of the silo, you've got a sump pump, which keeps the silo dry from all the groundwater. And so my assignment wasn't even actually on the sump pump. I was a systems engineer for the training device for the sump pump. So I'm really starting at the bottom on ICBMs here. And just to sort of move to the future, when I retired in 2014, I was the Northrop Grumman manager for the guidance system, and I was teaching system familiarity to the civil service on how Minuteman ICBMs work, the entire general familiarization of the missile, the silo, the launch systems. Because again, like I mentioned earlier, if you're working in the computer and you're working in the software, you're learning all the systems. And that's what happened to me after about a year and a half of working in training devices. Somebody came up with this tremendous idea. They said, why don't we take everybody in TRW and the government and the associated contractors who work on guidance stuff and put them on the same team. So this is, the year is 1987. And that's what we called it, a guidance cell. And it was this brand new concept of, let's have an integrated product team, only we didn't call them that yet, where you take everybody who knows something about the product you're trying to maintain and you put them on the same team, put them in the same building, have them all working together. And so that sort of flashes back to that chart where I talked about people. You have to organize your people in such a way that you're not wasting a lot of effort. And so I got to be in on the ground floor on the guidance cell, the guidance IPT. And my assignment in there was to be the expert on the D-37 computer in Minuteman. Now, this is the first digital computer to be placed inside a missile. And by going from analog to digital, you had the ability to reprogram to deal with retargeting and things of that nature. And so we're talking about the same technology that we were putting into Apollo at the time. And in fact, we sustained this computer up until about the year 2000. Apollo era technology we sustained until it just got to be too expensive. And now we've replaced all of that computer and guidance electronics with newer. Remember, we did this in 1999. We replaced it all with 1980s technology. Why do you do that? Because you have to be able to take technology that's available and works and can withstand nuclear attack, be hard against a nuclear attack. So I'm afraid to tell you that your cell phones aren't going to survive an EMP, but the new Minuteman electronics will. So this chart here, this is of course the D37D computer, and it's got a whole bunch of 33 different cards in here, most of which contain Texas Instruments NAND gates. And so if you were to dig down in there, hopefully some of you either have the experience or have learned a little bit about machine language and assembly language. If you're doing machine language, you're getting right down into that computer chip and making changes and creating your program to be the most efficient possible. Imagine then that chip. Nowadays, we have the registers and all of the math functions inside that tiny chip. I mean, back in the days of the Z80, TRS-80 computer, that's what we had back in the 1980s. Well, if you look at this miniaturized onboard missile computer, those NAND gates were basically fulfilling that function. They had, they did all the math, and then you had a rotating disk right here that that was your memory. And one of the unique things about this D37D, being one of these first super miniaturized computers, is that the disk would spin, but the read and write heads were fixed. And so when you wrote the software, you had to write your software in something we called word times, so that when your software got to the point where it needed a bit of information, that's when that disk was going across that read head. Or when you were going to go write a bit of information, that was when that disk was going against that write head. And so it's very interesting software. To say all that, to say that it was also presented an interesting challenge for sustainment. Perhaps some of you have heard of the guidance repair depot at Heath, used to be Newark Air Force Base, Ohio. And that's where we would send these things to be worked on. One of the nice things about sustaining this guidance system was when it was in the silo, it was ready to go, turned on, and we were pulling information from it continually. And we had a team of analysts who kept an eye on it. And usually, if you got a red light, green light on your guidance system, you could pretty much trust it, that if it said it was bad, it probably was bad. If it said it was good, it probably was good. But we had this team of experts that would dig down deeper down that rabbit hole to make sure that they understood, why did it say it was bad? Why did it say it was good? And that team, on a fairly often basis, would save us from having to pull a guidance set from the northern tier and get it back to Ohio to be fixed, because they could see what had triggered that red light, and they knew what they could do, leaving the guidance set in the hole to get it working again. Sometimes the opposite would occur, and one of our very smart analysts would look at that data and say, I know it says it's good, but it's not. We need to pull it. And so that's a part of sustainment, and digging down and going down that rabbit hole and understanding what's going on. Another big important part, which I don't hear talked about enough, is when you're in the development stage and you're in production, you have instituted a program. I think they I think they still call it FRACUS, Failure Reporting and Corrective Action System in the production facility. And what we did was we made sure we had that same system in our repair facility so that we would learn things about emerging degradation modes. If you've got a very efficient remove and replace repair facility, their focus, their mission is to cheaply, affordably as much as possible, repair these very complex things. And so therefore, they don't have a mission to dig down and look and see why it broke and whether the thing they were fixing actually was the thing that broke in the field. And so you had to impose that from the program office and say, we need to gather up this information. And so this is, for instance, one of the things you would think about when you're creating your system up in commercial space. Are you going to be able to see what's going on? Are you going to get that telemetry back that tells you what if it gives us a red light? Is there a way we can just turn it off and turn it back on? That's a fairly common understanding of space systems. But what about repair systems? If you're going to be doing repair in space, then remember, as you're building up those initial requirements, not just to find the cheapest, most affordable repair in space, but also to make sure that you understand the diagnostic and see if it's telling you anything about what your other systems are about to experience. So you don't go ignoring the early part of that exponential and finding yourself in deep trouble a few years later because there was a little bit of information you could have found cheaply, but you just didn't look for it. So that's enough for that chart. Let's move to the next one. This is my suggestion for books that you, if you have an interest in ICBMs, I would start here. The Command and Control is not only a great book, but it's also a movie you can find. I think it's still out on Netflix, but I'm sure you could find it somewhere if you want to see and hear more about. This was the days of the liquid-fueled Titan and the analog computers. We had a couple, 3 disasters that that were just terrible loss of life. And because the liquid-fueled system is very difficult to sustain, very difficult to operate, and can result in some very horrible disasters for the people working around it. When we went to the solid-fueled Minuteman, that was a huge improvement in terms of, in fact, that's why they called it Minuteman, was because it could launch on a moment's notice. You didn't have to go through a lot of defueling and refueling operations like you did with the liquid-fueled ICBMs. But let's move forward. I showed you this chart earlier where I said I entered the fray around the mid-1980s when we were going from rapid prototyping a lot of different ICBMs to where we were, let's see, I'm pointing my cursor in the wrong place. We were rapid prototyping a lot of ICBMs. We went to just basically sustaining Minuteman III for decades. And I put this chart up again to say that, of course, that wasn't the only system that was deployed. For instance, Minuteman I was deployed back here in the 1960s. The B-52, the KC-135, they came out in the 1950s, and they are still flying today. And in fact, when I flew the KC-135 back in the late 70s, early 80s, people were already making jokes about how old it was, and they're still flying it today. We were already having emerging failure modes that they never thought of in the failure modes and effects analysis book. Like, for instance, we landed in Hawaii one day, and there's this pipe that comes out of your hydraulic pump on each of your engines to power your hydraulics in the KC-135. And one of those pipes had split, just blown open because of the weakness over time of that particular material. And it's kind of a freak. They dug into it a lot and decided that that was just basically a one-time issue, and they didn't have to worry that much about replacing every pipe in every tanker. But that's the sort of thing that you have to ask that question. And it was definitely not a failure mode that they were expecting would be something that you would have to track over the life of that tanker. But and also I remember anytime I flew a KC-135, especially as the aircraft commander, if nothing went wrong on the aircraft mechanics or systems throughout the flight, I would get more and more nervous because I was convinced that every flight of every KC-135, something would break. And if I didn't see it, then that might mean that it was a system I cared about that I didn't notice it broke, right? So that was just the mindset. I'll just throw in another idea here about the KC-135 because of this idea of continuous sustainment. During the period of time when I was a pilot on KC-135s, these engines, these are the old J57 engines, water injected to get enough thrust, and you know, the best we could do, really quite advanced for the 1950s. But you know, the sort of a downside to these jet engines was they would blow up, which is really inconvenient if you're trying to fly your airplane. We would spend a lot of time practicing, you know, what we would do if one of our engines blew up at just the wrong time. And some of the engineers in Logistics Command came forward and said, you know, we think that given the instruments on board the aircraft in the cockpit, if we could just get the pilots to record the information on those instruments, we could come up with a way of predicting when the engine's going to blow up and avoiding you know, that happening to the pilot. And you can imagine probably if you've ever been in the military, when the engineers impose that on the pilots, we do what we always do the best, and we groused and complained about this huge workload that we suddenly had to take on, which actually was nothing. But we, you know, we needed something to complain about, and we did. But then after a few weeks and months of doing that, we started to notice that the engines were not blowing up anymore. And then we became, you know, the people that were the biggest converts to this. Let me move forward. I notice I'm sort of spiraling out of time here. I like to include this chart just to say that part of our task as ICBM engineers was to support the removal of nuclear weapons and ICBMs from the arsenal. And I think we did a pretty good job of that too. Here's our definition of complex systems and systems. So system is a construct of elements that produce results not obtainable by the elements alone. So remember Oliver Evans' flour mill, where he had introduced some new pieces and put them together in such a way that you've got much higher quality flour coming out of your flour mill that you never would have gotten had you not gone to a system. And then complex, of course, means that complex means that you run the danger of having your system enter a state where you were not expecting. So that's why we invented failsafe. Let's move forward and get to sort of the heart of what I came here to talk about. These lessons. So for instance, early detection, I told you the story about the battery and the piston and the yellow powder already. Indenture, if you're going down your indenture and looking at individual piece parts, that creates this requirement of determining which things need to be serialized to be tracked individually. And that list of things that were serialized actually grew over the lifetime of the ICBM. And that's something to think about when you're creating your system, of course, if you've got the opportunity, and we do nowadays, to individually serialize every single item so that we understand if you have a dozen of these from this lot, maybe you've got a problem. And then I wanted to tell the story about the teamwork. And I mentioned the IPT and the guidance cell, but let me tell another little story. which we would tell each other all the time at TRW ICBMs, and that is the story of the engineer and the statistician. We have a wonderful statistician, top of his game. In fact, we had a team of them, but this particular statistician decided that he could really come up with a great thing. He went and looked at all of the data he had on this particular battery, and he applied all of his statistical knowledge to come up with the perfect fit of how that battery would degrade over time so that we could do a much better job of sustainment. And in all eagerness, after working on this for several days, he took it to the top battery guy at TRW, showed it to him, and that battery guy said, "Man, this is fantastic work. I understand everything you're telling me. This is wonderful. The only problem is that batteries don't do that." So that the lesson is you can't just grab the data and model it. You have to understand the physical activity occurring behind the data, which means that your minimum size team is one engineer and one statistician. And don't think that just because you're a really good engineer, you're a good data analysis. Don't think that you're good at data analysis leads you to know everything that the engineer knows about the device. But that expands into the whole IPT. You have to have that teamwork to make this work. I'll just go to one more chart before I throw things open to a bigger discussion. I've got this chart where I talk about, okay, what does that look like in space? I've already mentioned this idea of remoteness. Age surveillance, we would take a whole bunch of fourth stage. And when we built all the liquid fourth stages for Minuteman III, we built extra, put them in a warehouse using the exact same conditions they would experience in the silo. And then every year or two, we would pull one out and thoroughly go through it. And that would save us from having to grab ones from the field. CLFA I talked about, that's the one where, get the big arrow here, that's the one where you're looking at the repair depot. In production facilities, they called it fracas. In repair facilities, we called it CLFA, closed-loop failure analysis. And I've got a presentation on that too that goes into a lot of details. But the bottom line is the biggest loop you're closing is the one that says, is the thing I fixed, is that have any relationship to the thing that broke out in the field? It's amazing how powerful that single question is. Then we have a lot of excitement right now about digital twins and systems engineering using a lot of computer models. And I'm all for these new models and I'm excited about using them, but you have to understand their limitations. And again, you have to be concerned about whether your digital model has really captured everything, including things that might be emerging failure modes that you weren't expecting to happen, like for instance, maybe your hydraulic pipe blowing open that you forgot to put into your failure modes and effects analysis. So my contention is that you might not be finding your emerging failure modes if you're depending too heavily on your digital twin. It's at least something to think about. And then another example I threw in here for the benefit of discussion. There's a lot of things we could talk about under teamwork, but I was very impressed by the folks putting together the Ascend conference at AIAA. That's used to be space, and it's another conference too. They combined them, and they said we're looking at space today and tomorrow, which means a lot of commercial space, which means our IPT is much bigger than you think it is. And they were inviting people like people who ran hotels to come and speak to them at the Ascend conference, so that you make sure that you do have that big teamwork. I mean, here's one that my pet peeve all through the time I worked as an engineer. I think we didn't give librarians enough credit, and every team I think should have had somebody who had studied library science and knew how to collect and find things right away. Of course, it's probably because my mother was a librarian. But so I've got other charts here, like for instance, some pictures I've used on my commercial, some more points to be made about things like climate and COVID. But I think we're probably to the point where we want to Oh, and here's my my science fiction ending to my discussion of commercial space. You know, could possibly turn into a battlefield. We need to think about that too. But let's go ahead and call it a day. It's 8:30, and if people have questions, I didn't let you really throw in and discuss things. So I should let you do that now. But these charts are posted. And so let me just say that if you pull up these charts, you can see what's out at my website, my published papers. You can see the IUS missions and a little bit, I think, here about ICBM. So anyway, let's throw it open to questions at this point. And I hope I didn't ignore you when you were trying to ask a question earlier, but if you still remember it, go ahead and tell me what questions you have.
Well, thank you, Charles. It was a very good presentation, and I appreciate the added information, especially identifying the difference between sustainment and sustainability, which I learned now, and I kind of understood that before, but it kind of gelled in my mind now that you brought it up. You might be like me, and I'm also retired risk manager, and I kind of look at the world through risk management eyes and apply risk management principles to almost everything I see. And you might be doing the same thing in your view too. And one of those things was the Boeing 737 MAX disaster. And if you remember when that happened, why Boeing came out and said, "Oh, it's a simple little software fix, and we can fix that in 4 lines of code, and then it'll be okay. And we can put these planes back together and manufacture, 2 a day or something." And then they found out some other things, and through congressional hearings, they lifted up the rug and they found more spiders and snakes than they thought they had. And every time you looked at it, you found something new. And you kind of wondered, well, how could all these unbelievable bad things end up in the plane even flew to start with, And I don't know if you saw a recent broadcast called The American Greed. It's put on by CNBC.
I've heard of it.
Yeah, and they had a broadcast about a month or a month and a half ago about the 737 as an example of American greed. And the theme of the whole show for an hour was that the Boeing had agreed to get to get this plane up before their competitor got their version of a new plane up, and they wanted to make more sales and make more profit. And so that's where the greed came in. And that caused a change in the culture at Boeing. It may have started changing before that, because the push at Boeing, I never worked for Boeing, so I can only talk about what I've heard, on reports and stuff.
Well, let me just say that I was profoundly disappointed in Boeing because having flown their aircraft, having worked on their missiles, they were fantastic. I mean, the coming up with the B-52 design over a weekend, and having it still be out there today, yeah, it was a great disappointment that they somehow lost that culture.
Yeah, and this program, American Greed, addressed that loss. And that, like you say, the early days of Boeing, they produced some amazing things in short time. And that company was regarded as one of the best American companies, especially in aerospace. And so they said, well, how could so much go wrong on this one plane if that's such a good company? And then digging and digging and digging, they found out that the culture in the workforce changed in the recent years.
They've had nothing but trouble with their new KC-46, with their space program, every major thing they've worked on.
Yeah, and 787, and everything was coming out with failures and poor quality. in terms of sustainability design. And so you ask the question, whatever happened? Well, what they found in interviewing workforce is that the old workforce, you had engineers in there and they had questions about something. Oh, this doesn't seem right. There's gonna be a problem here. And so the management would take that very seriously, and they would delve into it and go down the rabbit hole and find out what the basic, the root cause of that concern is and fix it. Well, that takes a little bit of schedule, time, and a little bit of cost. And then the change in culture was, profit is the first priority. And so if you have a question about something that might be a little bit off, don't worry about it. We'll take care of it. It'll be fixed downstream or something. But if it's going to hold up schedule or cost more money, then it's going to be a concern to decide whether we should do anything about it or not, and most likely not, because it's going to cost schedule, and we need to get these planes.
We had a saying in ICBMs, if you think it's expensive to fix now, wait till you try to fix it later.
Yeah, right.
It's going to be really bad.
And the same thing with the 737 MAX, look at that. So what happened is the engineers suddenly decided, well, I can't bring this little concern up because they're just going to push it under the rug anyway, and right. I'll get reprimanded for trying to hold up schedule, or my work will be holding up schedule, so I can be reprimanded, and I don't want to get reprimanded for that, so I won't even bring it up. And so that was the cause of the change of culture, that you had the people in the work line down in the engineering workforce. They decided to not do the kind of inquisition that they had before to their own self, and therefore a lot of little problems got left undone, unattended to.
Let me
got buried.
The same idea and apply it to something like, for instance, climate change. So you have people who come forward to, you have scientists and politicians and everybody saying, well, we've got this major issue. And then you have somebody come in and say, well, I don't understand, first of all, why you say it's a major issue. You haven't explained it to me well enough. And two, the thing you're telling me that will fix it, doesn't seem to me like it's gonna fix it. And the response, generally speaking, has been, you need to sit down and shut up because the world's coming to an end. And that's not the way to solve the problem. I mean, that's the opposite of that is science, right? And you've seen some of the same things happen with the COVID pandemic. Well, you just need to sit down and shut up because we know what we're talking about. And the guys who say that usually are the ones that feel a little bit anxious about whether they really do know what they're talking about. They don't want to spend a lot of time in discussion because their ignorance might be revealed. And that's been my experience throughout my whole career, is that you get into a conversation with an engineer, for instance, about a particular thing, and if they start to get mad at you, the thing you should realize is, here's a human being who's worried that his ignorance is about to be revealed. It's nothing that I've done wrong. We need to continue to dig into this. Let me show you another example. Oh, it's backwards, I guess. Truth, Lies, and O-Rings by our local engineer here, Alan McDonald. And if you want to study another, where things went really wrong, Richard Feynman, the famous physicist, has an autobiography where he includes that whole discussion. And he was on the failure review board with my old boss, General Katina. And you remember the classic time where he puts the little O-ring in the glass of ice water, and that's same sort of thing. I hesitate to tell you that I'm teaching you lessons learned with sustainment, because we were constantly relearning. Oh, we dropped the ball there. But if you've got a sustainment model that you're trying to follow, you at least have that extra leg up where you say, oh, here's where we fell down. We didn't have enough tests on this equipment, or we didn't take a look at how this was being repaired. You know, at least you've got a model in your head of what went wrong, other than, you know, we've got yet another crisis this month. Let's go deal with that crisis and not go change our processes.
Right. I think you should teach a course in this subject area, but not at a university, not in high school, not at a university, but at a how do you put it? At a industrial setting where people come in that have had some experience, at least a 2 years experience, because it takes a little bit of experience to understand the human side of things and the human culture that comes into play when you're trying to decide and make a decision whether something little is important or whether it's just something you can forget about. And you can't teach that in college.
Well, I've done tutorials at conferences, and I've offered myself up to teach, but I think what happens is, I'm just guessing here, you know, other than just, you know, being swept up in the day-to-day and bringing in somebody like me to teach is not something people do as a normal course of work. But I think the other thing is that once they sit and listen to what I say for an hour or hour and a half, you know, I've got presentations where this is all I talk about. By the end of that, their first reaction is, "But this is so simple." You know, and
So obvious.
the sustainment model has to be simple because it's got to stay in your head every single day, and you have to think of it every day. So yeah, it may be simple, but if you're not thinking about it, you're not doing it, and you're getting into trouble.
Right. Exactly right. So yeah, it's all good stuff, and it's really applicable to any age and any company doing anything that produces a product or a service. And so it's something, you know, it should be made available to all kinds of industries, and not just through aerospace and ICBMs and aircraft, but through other things that they do also.
So I
Climate change.
gave a presentation about 5 years ago under, I'm also a member of the systems engineering.
In COSI?
Yeah, in COSI. You know what, everybody knows what in COSI is. I should just say in COSI. So I gave a presentation at the Great Lakes Conference, and on this subject talked about ICBMs and sustainment. And of course, there weren't really that many weapon systems folks at that conference. There were people like the big companies that manufacture the tractors, train air conditioning, a lot of civil systems. And they were pretty excited because they were just entering the mode in the last 10 years where their CEO had turned to the engineering department and said, you know, I think we need to get some of this systems engineering stuff in our company. Go do that. You know, and so they were really starting to pull in a lot of systems engineering to these civil systems, but they had not yet started to think in a systems engineering way about the fact that they had, you know, tens of thousands of complex systems across the country and around the world that they were trying to keep going. And so they went away from that to try to think about their sustainment in terms of systems engineering. Any other questions out there?
Thank you, Charlie, for presenting and emphasizing on the both sharing your knowledge and emphasizing on the importance of systems engineering approach, that interdisciplinary approach when you connect or look from the perspective of systems, especially when it's a complex system, is extremely important and very often getting overlooked. And especially when they're looking into a more narrow scope versus to impact overall to the whole system.
Could I just say one more thing?
Absolutely.
Since Mike gave me so many compliments, it really made me feel good. I want to say that risk manager in our IPTs, that was a special skill. And, you know, every once in a while, our risk manager would say something that would just kind of like, oh, yeah, you know, and I wouldn't have thought of that because they're looking at it from the point of view of risk management. So part of our structure of our IPTs was we would take fairly young engineers and throw them into the deep end of being risk integrators, where they would go around and talk to all of the senior engineers about what they might see coming up as problems in the future. And they would start to get a feel for what risks they might need to write up and present at their level of a risk management board to decide which ones are going to go forward to our risk managers and our tier 1 managers. And so that was a fantastic opportunity for some young kids to really to learn quickly about not only the risk management, but meet all these engineers and get a good background.
Right. I mean, I see one thing about that, and that is, in my experience, I have found that the most successful programs always had a risk management individual or team working with the risk management side. And some programs that would fail would have managers of the program that identified themselves as the risk manager. And one program I was familiar with was in a very secret, confidential setting, and the program was failing. And so I went to the manager of that program, and I asked her, what do you think is missing in your program that's causing all these problems, and you're really in a spiral downhill move here, and could I find out what you're doing about risk management? And she said, well, let's set up a meeting, and I'll show you what do we do about risk management. And so she set up a meeting, and she had her staff there and me, and the bottom line is that she was the risk manager. And I asked her, well, how do you identify risks? And she said, well, when I go to meetings and I see something doesn't look right, then I write it down in my little notebook here on the back page. And so when I go to another meeting, I flip the page over and I see my notes, and then I could tell what to bring up at that other meeting, and then find out how to handle that particular concern, which was risk. And I said, well, you never have a formal risk management meeting to identify problems and bring them up in front of the whole group on a regular basis. Oh no, we don't need to do that. That takes too much time, and it's too much work, and I can do it myself. Well, her program did fail, and a lot of people were laid off in months later. But the bottom line is, what I'm saying is that a lot of failures do occur in the risk management area because managers think that they are the risk manager, and they can do it themselves.
You know, when you have a risk management board, so for instance, in ICBMs, typically it would consist of the risk manager who ran the board. Then you would have all of the government and all of the contractor bosses in charge of propulsion, guidance, ground systems, and reentry systems were at that front table. Very important dynamic. You held it every month, no matter what, showed people it was important. When somebody came forward with bad news, the managers did not yell at them. They asked questions, tried to draw them out, tried to understand what was going on, and thanked them for bringing the information.
Right. And in doing so, you either find out that it's trivial and it's bad news, but it's not, it's kind of a manufactured bad news. If somebody thought something and it kind of blew it out of proportion. And so by asking those questions among the interdisciplinary people, you kind of melt that out. And the important thing is, if it's not a manufactured concern, and then you actually do have a concern, then the interchange between those interdisciplinary people will unfold that and identify it. And then you have a a way of fixing it, sometimes the way of fixing it is obvious, but sometimes you have to appoint somebody to go take a deeper look at it and then come out with some suggested fixes.
Yeah, so
And,
sometimes, like for instance, somebody at the table might say, hey, Bob, don't you have those same integrated circuits in your system?
Yeah. Yeah,
Charlie,
so
Charlie,
go ahead.
Ellen was asking, is asking in the chat if you heard about the Villanova green tail theory. Do you
I have
know?
not. I have not. Will she tell us about it?
I will. Let me turn on my video. Okay, so Villanova says, can you hear me?
Yes.
Okay, but Villanova says if someone comes to you and tells you about a problem, you can say, oh, that sounds interesting. You can kind of look around a little bit, but you don't have to be super concerned. The second time someone comes up to you and says, you have a green tail, you need to be starting to look around a little bit more seriously. And the third time someone comes up to you and says, you have a green tail, you need to stop everything you're doing and find the green tail.
So I guess it's a theory of three. So if it's a one, it's just a forewarning. A second is kind of taking a little bit serious, but still continuing your operations. But on the third warning or a third notice, you have to do a work stoppage and address appropriately the problem.
Exactly, Ellen, and what you're saying is does apply to risk management in that usually the probability of impact to your program is observed very far away in a very small way, but by one person maybe. And then in time, a second person, maybe not even connected to the first person, identifies something connected to that same risk. And so the probability starts to grow. And then a third person comes along and says something else that's independent of the first two, but happens to be a same kind of concern. And then the probability starts to grow very, very large. And a good risk manager will notice this and elevate the probability of that, and then it becomes elevated. So the red flag gets higher and higher on that pole, and then some action can be taken. So that's a good theory to look at, a good way to look at it, the 3-point theory.
Okay, any other questions for Charlie? It's a great discussion, and Mike, I'm sure we will follow up in one of our free form with no speaker, because it's quite important for the engineering, for systems engineering. Okay, Ellen, I think Ellen is signing off, and a few others signed off. Well, I wanted to express thank you for Charlie's appearance. And Charlie, if you have on other days, on other Saturdays, time and desire, you are welcome to join us, because as I said, that we hold this gatherings every Saturday. And on some we have speakers, and on others we just have a free form discussion, and one of them could be a risk management or overall the systems approach. And you are welcome. Your the wise input, it will be always welcomed and appreciated, just like Mike's.
I enjoyed it.
Okay, well, thank you so much, everyone. And I'm going to close our session for today. Stay safe and be happy, and have a great week.
Aloha.
Thank you, Svetlana. Oh, Svetlana, before we go, can you tell me if we have a general Zoom link that we meet at for Saturdays when we don't have speakers?
We actually, this is the same link. We are using it every time. So if you have the link, basically you have access to every Saturday. So it's the same link. I'm for the general sessions when we do not have a speaker, I do not send a reminder, but nonetheless, we always have this meeting. So, and I'm
Yes.
telling you, it's possible because I am joining everyone from Hawaii at the moment. So it's the link
Oh.
works everywhere. Yes.
Awesome.
Okay.
Okay, thank you, Svetlana. I was under
Great.
the impression that we were only meeting with speakers now, and so I was kind of sad about that. I was like, oh, we're not meeting
No,
every Saturday?
we meet every Saturday.
Okay, good. All right, thank you,
Okay.
Svetlana. See you next Saturday.
Thank you.
Bye-bye.
Bye,
Hi, Carol.
guys.
This is Carol. Thank you,
Hi.
Svetlana.
Oh, you're welcome. Thank you, Carolyn,
Yeah.
for joining.
Yeah, and Charlie was great to have him 2 weeks. I really appreciated that. I think he's left, but let him know.
Yeah, I
I'll
think
thank
he's
him
left.
again.
Mhm. Okay, thank
All
you,
right,
guys.
well, enjoy your holiday.
Bye.